Right. There's maybe a few things going through your mind right now. One of them might be, why am I wearing a dicky bow? And I don't really know. I just saw it and I was like, today's a dicky bow kind of day. The other one might be, why have you got your hood up? Well, originally I wasn't going to do my hair, but then I did my hair, so it's all right. But I'm kind of thinking about growing my hair out so it looks a bit bush. Similarly for the, I don't know what's going on visually. But let's do some differentiation, okay? Okay, what we need to do is we need to think about what actually is differentiation. So this is a major topic in mathematics. It's under this umbrella of what's called calculus, which is essentially the mathematics of change. Now that might seem a bit weird, but it's actually what I consider one of the 4 pillars of mathematics. We've got numbers, just basic kind of number theory, algebra, geometry, and then finally, your little pinky swear, we have mathematics of change, i.e. calculus. Let's get that written on. I didn't underline the title. Gone for a fat underline. Okay, so mathematics of change. Let me just do this little disclaimer now. I haven't planned how I'm going to use the chalkboard. This might be absolute sheer chaos. Let's continue and see what happens. So, calculus is the mathematics of change. It was invented in like the 17th century by a couple of mathematicians. I'm not going to say the names because I want to steer away from this history of who did what, because it kind of gets into the whole lines of, oh, it's an old white man. So if we just say about that someone did it 17th century, there was a lot of disagreement about who was the person who originally did it. And that's all we need to know. But because there was multiple people involved in the creation of this topic, we see a lot of different mathematical notation from this. And we're going to use most of them. Don't know why, we just do. Okay, so the mathematics of change. What do we mean by change? Change is like x over y. No. Change in y over change in x. It's gradient. How does something change as something else does? We might be thinking of something like miles per hour. How many miles per hour do you do? Or we could just think in the sense of mathematics as in coordinate system, cubic. How does it change? What's the gradient doing? Now I'm going to backtrack a little bit and draw a few little graphs for us to look at. All right, observe graphs. What we have here is a linear graph. I hope you can see that yellow. Oh, yes you can. Right. This is a straight line. If we were to say, right, what's the gradient of this? Okay, gradient is, well, let's say m. Back from our old little simple coordinate geometry. Change in y over change in x. If I take one step in the x, how much has it changed going up? And if we did this, we'd take like a point, say here, we'd take a step across, we'd go up, we'd do, that's change in x, this is change in y over change of x, that's your gradient. If we kept doing it, we'd realise it's the same everywhere because it's a straight line. Its gradient, or its slope, is constant. So if we were to do this thing called sketching the derivative, which is to say, we're going to plot how the gradient changes with x. Derivative is another kind of word for the gradient function, how it changes with x. So if I was to look here, okay, at this value of x, the gradient, well, it's positive because it's going up. It looks like it's less than 1, so I'll put a little cross there. Let's do it in yellow. Right, move along a bit. Well, the gradient's the same there, so let's do another one there. Move along another bit. Let's go to x is 0. Well, the gradient's the same there. Let's skip along to here. Well, at here, the gradient is, well, it's still the same. So, ooh, this is the derivative. Let's get that written down. Sketching the derivative. This is the derivative of that. And I'm going to make a little note. What is the derivative? Well, it's the gradient. Specifically, it's called the gradient function. Now, if we look at a line like this, you might be like, why is it a gradient function? It's just a number. It's constant everywhere. Well, let's have a look at this nice little quadratic. If we were to look at this, we'd be like, okay, so if we looked at this little point here, the curve is actually going down. So what we're interested in is the gradient at that one point here. Let's do a bit of white on here. The gradient at that one point is the gradient of the tangent at that point. So if I drew on a tangent, there we go. And if I took the gradient of that, I did change in y over change in x, so change in y over change of x, found a number for that. Right there, I'd see that it was negative because it's going downhill. Okay, so at this value of x, let's put it there, it's negative. How about here? We'll look at this point here. Just going to hold that in my mouth then. Right here, look at that. If I do the tangent there, at that value of x, it's still negative. That tangent is still going downhill, but it's not as steep as it was there. So what we're going to do for this value of x, we're going to put a little coordinate in. Whereabouts was it? It's kind of at x equals 0. So it was still negative at x equals 0. Right, so I've got 2 points. I could attach another one and stick that in, but that's that. Now let's have a look here. This one's an interesting point because if I do a tangent here, right at the bottom, at the vertex of the quadratic, well, that's a flat line. And we know that the gradient of, I've not done that. The gradient of a flat line, well, it's just 0 because it's not going up, it's not going down. The gradient is therefore 0 because if you took one step to the left, it sounds like I'm doing Mambo number 5. If you took one step in the x direction, you go up in y by, well, you don't change in y. So it's 0 over something, and that's just 0. So the gradient at the vertex of a quadratic is 0. So here we are, right? I'm going to go this value of x, the gradient is 0. All right, and now we're on to this side. Look at this. As soon as we've passed the vertex, we've now got a positive gradient. Positive gradient, so I'm going to do this on the positive side of here. Ooh, interesting. And if I'll put it down. I need that one. And if we move along a little bit more, ooh, it's more positive. In fact, it's just going to get more positive until it's like near vertical. So this will go somewhere like that, and then we'll connect these dots. And if you've done it right, what you'll actually end up with is a straight line. Now what this is, let's just mention now, this is your value of x. This is m. M is your gradient. Now, what we'll see as we do differentiation as a subject is that we're not going to write it as m anymore. M is what we say when the gradient is constant, but this is clearly changing. As when x was negative, m was negative. And then over here, when x was 0, m was still negative, but less negative. Then up here, it was positive. So what we see, that this, which is the gradient of that, changes with x. So what we can say is a definition that the derivative is the gradient function. We have a function, but then if we look at the gradient of that function, it also changes in x, and therefore we call it the gradient function. We have a little bit of notation for that. The notation that I'm going to introduce now is that if we call our original function f of x, so we just put, like y is f of x equals, I'm going to try and do this. I think if you plotted that in something like Desmos, it will look quite a lot like that. I'm using my knowledge of where the vertex is and completing the square. Right, if this was our function, x minus 1 squared minus 2, it's quadratic, then our gradient function is that. But we don't write an m anymore, we write this. Oh yes. Oh yes, let's get a closer look at that. What this is, my friends, is an f with an apostrophe just after it. We pronounce it f prime of x. And it means the gradient function, aka the derivative. Oh yes, we have arrived. This is differentiation. The whole point of differentiation is to find that. And what we have is a load of rules which we get from something called first principles, which I'll do in the next video. Right now, we're just interested in sketching the derivative. Technically, this title of the video should have been sketching the derivative, and I was kind of confused as to whether to do that or not, and that's the side point. Blah, 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 blah. Let's do some maths. Right. We've got a cubic on our hands, so let's just do this cubic right now. We're going to be fast about this, fast as lightning. This is f of x, that's x. We're going to plot x and f prime of x, the derivative. Oh boy. So to do this, what we're going to do is we're going to draw little tangents all over. Right, tangent, there. So at this value of x, our gradient is positive because it's going uphill. So let's just put that about there. All right. Then as we move on, we're getting closer and closer to 0 until there. Ooh. At this point in x, that has a gradient 0. So right down here, we go to 0. Now remember, the y-axis here doesn't represent our function, it represents f prime of x, which is the derivative. So I've gone down to 0 on the y-axis because that means we've got a 0 gradient. Okay, once we pass that, we go, oh, we start getting a negative gradient. So we've got a negative gradient, but let's not draw any tangents yet. Negative gradient, then it gets to here and it starts going less negative. So it's most, let's just draw a couple on. I don't know if you can see them on that camera, but we've got negative, but not very steep. Negative, a bit steeper. Negative, as steep as that one was up there. So it kind of goes steep down to its steepest point, and then back up towards, towards a 0. This ruler is remarkable. Look at that. So how we're going to do this? So this is a bit tricky. We go down, then it goes to its steepest bit about there. That's the steepest it's going to be. That's going to be the lowest gradient, like most negative gradient ever. Then it goes back up, and it goes to 0. All right, nice. We're getting there. And then on this side of the, can't call it a vertex. I'm going to call it a minimum, even though I don't know if you've ever come across that word yet. Okay, so then we go there, it's positive, then it gets more positive up there. So it's going to go I'll go. Hey, there we go. Now, those plots, those pots, those points on this plot, they look like a quadratic. In fact, they are a quadratic. And that's an interesting point because I don't know if you have, but if you do the derivative, sketch the derivative of a linear, you get a flat line. Sketch the derivative of a quadratic, you get a linear. Sketch the derivative of a cubic, you get a quadratic. Guess what? If you did the derivative of a quartic, now remember, I'll just sketch one quickly. That's the quartic. Sketch the derivative of that, guess what you're gonna get? Yep. It's gonna look like that. See, it's negative, it goes down, then it gets to 0, so that's gonna be where it crosses through the axis. Then it's positive for a little bit, so doesn't matter where this is on the coordinate system, but this one it does matter where it's on the coordinate system. So something like that. Now that's just a quick sketch. Something to note, right, is that we could move this up and down. It's not going to change the gradient. We could move it left and right. That would move the gradient left and right. But if we move it up and down, it's not going to change anything. So I could have had here, back to our quadratic, we could translate it in the y direction by adding some constant to the end of it. This is not going to change. If I translated it in the x, it would just move it from there. It would be over there like that. Right. I'm going to make some room on the board. Right. Well, we've got one last little example. This, as I'm sure you're aware, is f of x is sine x. Does that? What we're going to do is we're going to sketch the derivative of that. So let's get a little coordinate system set up. Remember, I've written f prime of x there. So we prime there. Sorry if you're Scottish and that offended you. I just like doing accents. Let's see, is my camera still going to record this? Don't know. What you should be able to do is use this technique to sketch the derivative of absolutely any function. Anything. No matter what I drew on the board. You don't actually need to know what the function is. You just have to know what it looks like. It could be absolutely chaos. But you use this little thing of analysing what's happening at the tangent, because that's the gradient at that exact point, and then just do a little sketchy-roo. So what we're going to do here is a little sketchy-roo, okay? Here, the gradient is, well, it's positive. So let's start down here somewhere. In yellow. There it's positive, so I'm just going to, okay? Then it starts to get lower and lower and lower and lower and lower and lower until it gets to, the 0. So it's getting lower until it gets to 0. So I'm going to do this just because I can. Right, don't know if you can see that, probably not. That's red chalk for you. So at this point, gradient is 0. Then it starts to get negative to, and it goes to a maximum negative, because that's as steep as it's going to get, and then it shallows out again. So at some point down here, it goes to its maximum negative, and then it starts to go back up to 0 there. Okay, then it goes positive, and it's positive, and it gets to a maximum positive there. So, right about there. And notice how the gradient of that bit, if you do a tangent there, the same as the tangent there because they're both parallel. Look, they're parallel. I don't know if you can see that because it is a sketch and it's not perfect. So this point here is just as high as that point, and then it starts to go back down to 0. Now, because I know that the change wasn't linear, it wasn't just like going to 0 and then went straight back down, the tangents weren't just doing that. It had a curvy curve. I'm going to join these up by doing a little curve in them. Right. That's it. And I could continue it back that way if I was to keep going, and it would go a bit like that. And then at some point I'd go, wait a tick, that's a cosine. And this is what we do in differentiation. We notice little rules and we move forward. But there's a way to mathematically prove that that is a linear and that a cubic is a quadratic, and that's what we're going to look at next, which is called differentiation from first principles. Because everything we do here, this is kind of common sense stuff, but it's got mathematical background and standing and foundations, and we're going to look at that next. What I recommend for you to do to try your own practice at this is maybe just go into Desmos, plot something, and then do the derivative of it yourself on paper, by hand. Yeah? Actually get a pen, some paper, maybe a pencil, right? If you don't have a pencil and pen, go get one. What? It's 2021, you don't have a pen and paper. Yeah. Right, good stuff. Bam.